right, so far we just talked about ionic compounds. Molecular compounds are compounds that do not contain any ions in them. So they're just molecules that are formed by sharing electrons. So in terms of molecular compounds, they form these very distinct units of bonded atoms, which we call ions. We call molecules. Ionic compounds don't form molecules because they're just a grid of positive and negative charges that kind of are self-organizing into this three-dimensional crystal array, but they don't form these distinct units. So you can identify a molecular compound because it's always going to be made from nonmetals, and those nonmetals will form covalent bonds. So the bonding is still going to be formed from the valence electrons, just similar to what I talked about in the ionic compounds. Okay, we still have these outer layer of electrons that are involved in the bonds. But in this case, rather than transferring the electrons to achieve stability, they're going to share electrons with each other to achieve stability. So when two or more atoms form a unit by sharing electrons, they form a molecule. So simplest molecule is hydrogen. Okay, hydrogen is formed from two hydrogen atoms. Okay, hydrogen atom just consists of a single proton in the nucleus and an electron moving around that nucleus. Now for hydrogen, they can achieve stability by sharing electrons with each other. So hydrogen are going to overlap their valence shells and share their two electrons with each other, forming a single covalent bond. In hydrogen, I think I mentioned talking about valence shells, and valence shells were stable with 8 electrons. Hydrogen and helium are the exception. Because these atoms are so small, they can fill up their outer layers with only 2 electrons. And they can become stable that way. Everything after that first row on the periodic table needs 8 electrons in their valence shell to become stable. So here's the 2 hydrogen atoms. They come together. They start to pull on each other's electrons. So the distance between them gets smaller and smaller. And eventually they overlap their valence shells and form a H2 molecule. And when this happens, the energy decreases. So the 2 hydrogens actually release energy into the environment when they come apart and they form a hydrogen molecule. That energy gets released into the environment. It can either be in the form of heat or light or a combination of the two. Here's another example. We have fluorine. So there's our fluorine, and these are the valence electrons on fluorine. So in fluorine's outermost layer, it has 7 electrons. So 2 fluorine atoms are going to come together, and they're going to share 2 electrons between the 2 of them. So right here, there's a pair of electrons being shared. Now there's also 3 other pairs on each fluorine atom that are not being shared. So the electrons that aren't being shared we're going to refer to as lone pair electrons. and the electrons that are being shared between the two are going to be called bonding pairs. We'll get to why we like to put electrons in pairs in later chapters, but just for now, just take that, accept that part. You'll be getting an explanation. So now, by sharing these two electrons with each other, they're completing that outermost shell and forming an F2 molecule. Now, these are examples of elements like hydrogen fluorine that also form molecules consisting of a pair. Okay, so when we want to diagram the sharing of atoms of different elements, we use what we call these electron dot formulas. We kind of it's a bookkeeping to keep track of the electrons that are being shared between two atoms and the ones that are not being shared. So here's an example. CH4, NH3, and water, H2O. So you see in this case, carbon normally has 4 valence electrons. And hydrogen has 1, so it's going to share each of its electrons with 4 hydrogen atoms. So as a result, we get this molecule where the carbon is bonded to 4 separate hydrogen atoms. And we form what we call a methane molecule. NH3 has 6, nitrogen has 6 valence electrons. 5 valence electrons, I can't count. Nitrogen has 5 valence electrons. So it needs 1, 2, 3 to get to 8 and become stable. So nitrogen, it will share electrons with 3 separate hydrogens. The hydrogens will donate, each hydrogen will donate an electron to nitrogen. And by sharing, they become a stable ammonia molecule. And then water comes from oxygen. Oxygen has 6 valence or outermost electrons. It needs 2 to get to 8. So by combining with 2 hydrogen atoms, it becomes stable and forms a water molecule. Okay, so just giving a little bit of background on bonding and molecules. I'm not expecting you to draw electron dot diagrams at this point. I'm just showing you how they're distinct from ionic bonds. In all of these cases, there was no transfer of electrons. We just had atoms sharing electrons with each other to form these very distinct units. Okay, so so if I look at this example, now each line represents a pair of electrons being shared. So with this hydrogen chloride molecule, how many electrons do you see being shared? Or how many pairs, I should say.
Two
electrons. So how many pairs is, that would be 1 pair, right? If it's 2 electrons, it's 1 pair.
Okay, sorry.
Now, how many pairs of bonding electrons do you see here in PCl3?
3 pairs?
Right, 3 pairs. 1, 2, 3. 6 electrons, 3 pairs. So now if we look at the pairs that aren't being bonded, we got 1, 2, 3 on the chlorine. None on the hydrogen. There's no non-bonding pairs on the hydrogen. And if we look on the phosphorus, we have a pair here. And then on the chlorine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 non-bonding pairs at all. So to figure out the valence electrons, we just count all the pairs and multiply it by 2. So we have 4 pairs times 2 is 8 valence electrons in all here. 10 and 3 is 13 times 2, there's 26 valence electrons here. Because remember, each dot is an electron, and then the lines represent a pair of 2 electrons being shared. Okay. So with molecular compounds, because of the many different ways we can combine and share electrons with each other, and in some cases, you can, if I have 2 atoms like carbon and hydrogen, there are literally millions of ways I can form compounds from carbon and hydrogen, just in the different ways of assembling different amounts of carbon and hydrogens. So when we name molecular compounds, we cannot just state the name of the 2 elements in the formula. We need more information. So with molecular compounds, we're going to use prefixes to indicate the number of the nonmetals. Now, mono is not going to be used if it's with the first nonmetal in the compound. Mono will be used if it's for the second name, but it's not going to be used for the first name. So here's an example. NO2, we're going to call that nitrogen dioxide. Now, if I look at CO, carbon monoxide. Now, similar, you'll see in English, when you have prefixes that end in a vowel, to avoid putting an A or an AO together, you usually drop the ending of the prefix and add it on to the end. So this becomes, instead of saying monoxide, we just say monoxide. Now, what would that be called? CO2.
Carbon dioxide.
Carbon dioxide. Okay, I cannot just say carbon oxide because these, when they share electrons, they're not forming charges. So I cannot, just by saying the type of atom that's combining, I can't, that's not enough information for me to derive a formula. So we need to give more information in the name. So these are the main prefixes you need to worry about, okay? Just 1 through 10. And for these prefixes, we're only going to be using them for simple molecular compounds. So these are molecular compounds that are formed with 2 elements. Okay, we're not going to get into complicated organic molecules because that's a whole different naming system. So these are fairly straightforward. Okay, CS2 carbon disulfide, CO2 carbon dioxide. Oh, I forgot to mention, the ending does change for the second element. NO, nitrogen oxide. You could also call it nitrogen monoxide. That's perfectly fine. N2O, dinitrogen oxide or dinitrogen monoxide is also correct. SiO2, silicon dioxide. SO2, sulfur dioxide. And then SF6, sulfur hexafluoride. Okay, so what would this be called?
Nitrogen chlorate? Fluoride?
Is it trichloride?
Nitrogen trichloride. Okay. Chlorate is a polyatomic ion, ClO3. Okay, so it would be chlorate. So we're going to need nitrogen trichloride. Now, this is not, I can tell this is in an ionic compound because it does not contain a metal or NH4. If I see NH4 or a metal, I'm going to assume this is a ionic compound, and I use the ionic naming rules. Because this does not have a metal, I'm going to use the covalent rules. So in that case, I need to use the prefixes. So I have nitrogen trichloride. Okay. So for molecular compounds that don't involve ions, we need these prefixes. Okay, so what would the formula for this molecular compound be? Diboron trioxide.
It'd be 2 boron.
Okay.
And
So we're
then-
going to put the 2 after the boron.
Yes, and then the O for oxygen subscript 3.
Right. We could just read that as B2O3. Okay. Now, gets a little now this is a combination of ionic and molecular compounds. So I'm just going to ask you, which one of these, do you see any compounds that are ionic? So you want to look
Is
for
ionic?
C is ionic because of aluminum. So that you want to look for metals if it's ionic. Any other ones that are ionic? See any other metals?
Oh, Ni is nickel, so D.
Nickel, that's ionic, right? So these are going to be named differently than these are. Different naming scheme. So for the top 2, we're going to use the prefixes. So this one we already named in the last slide, so we know this again. This is boron trifluoride. Anyone want to take a crack at B? What is OCl2?
Oxygen bichloride?
Oxygen dichloride. Okay. So C and D now, back to the ionic naming. So that means you just name the positive ion followed by the negative ion. So Al2O3 would be
Aluminum oxide.
aluminum oxide. Okay. Now, Ni3PO4. You might need to look at that charge sheet which I gave you. But I'll tell you what to look for on that. So if you pull up the charge sheet, you're going to see PO4 is listed as a polyatomic ion on that common ions list. That's on the first page. So if you can look for PO4, and you see it's going to be called phosphate. And PO4 has a charge of -3.
Can you remind me again why it's not phosphite?
Yes, phosphite has one less oxygen. Phosphite would be PO3. Ites have
Okay,
always
got it.
one
Thank you.
oxygen than eights. Yeah. Now nickel, excuse my penmanship, is in the middle of the periodic table. And did I give you help with that? Oh, I apologize for that. Okay, I didn't list nickel on my sheet, unfortunately, but I'll just tell you this. Nickel is in the middle of your periodic table. It does actually form multiple ions. So, which means nickel's going to need a Roman numeral. And nickel, if this is a -3, this has to be a +1, so it's going to be nickel 1 phosphate. I'll have to update that sheet to put nickel on there. Like so. How are we doing on time? Okay. Let's see, let me just double check one little thing. I'm going to